Welcome students. In this video we are going to talk about the imperfections in the crystal. Okay. So let us see the classification of these defects or imperfections. How this is classified. So first is the point defects. This is also known as zero-dimensional defect. Zero-dimensional defect, which are intrinsic and another type is extrinsic. In intrinsic we are having the vacancy defect, then we are having Frankel defect and the Schottky defect. In extrinsic we are having substitutional and interstitial defects. Okay. Then in line defects, that is one-dimensional defects, we are having the edge dislocation, then the screw dislocation. The screw dislocation. So this is a line defect. Third, we are having these planar or surface defect, which are two-dimensional defect. Here we are having the grain boundaries. Low angle tilt boundaries. Then twinning and stacking faults So these are the defects we are having in the surface defects. And fourth one we are having, that is the volumetric defect, which are we can known as the 3D defects. Take the example as a voids. Okay. So these are the defects in the crystal or the imperfections in the crystal we are going to see. Now see, when you talk about these zero defects, so zero defect में कौन से है? In extrinsic, that is the vacancy, Frankel and Schottky. So let us start and see it one by one. So we'll start with the vacancy defect. So how it is created? So let us see the vacancy defect. So whenever from the regular atomic arrangement there is a missing of the atom, okay, directly one atom is missing from this regular atomic arrangement, so defect is known as the vacancy defect. The missing of the atom from the regular atomic arrangement, it is known as the vacancy. This is the vacancy defect. Okay. Or misplacing of this atom from its position. So this is the vacancy defect. In intrinsic we again having the Frankel defect. So whenever we are having the ionic materials, so in that what is going to happen? So atom is missing from its position, but same arrangement it is taking some interstitial site. Okay, so from here it is getting missed, but it is again sitting in the interstitial sites into this arrangement is nothing but the Frenkel defect. So these are the defects generally seen in the ionic materials, where there is a large difference between these sizes of these cations and anions. We will get this Frenkel defect. And in Schottky defect, as if you have these ions and cations, anions, cations, big are the anions, smaller are the cations, we know it is, isn't it? So from this ionic arrangement or ionic material, so the pair of the anion and cation, this is the bigger one are the anions and smaller are the cations. So whenever the pair of this anion or cation together is missing, so suppose from here this anion and from here this cation is missing, then this defect is known as the Schottky defect. Okay, so these are again these defects are Frenkel and Schottky defects we are getting in this ionic materials. This vacancy defect, like same like this vacancy defect. So displacing or the missing of the single atom from this atomic arrangement, this is a vacancy defect. Here it is missing, but again going where interstitial side within that atomic arrangement, and here the pair of cation and anions are getting displaced or missed out. This is the Schottky defect. Please remember this. Now if you talk about these extrinsic defects, where we are having the substitutional defect. So here in this regular atomic arrangement, the foreign atom or impurity is going to substitute the host atom. Okay, so the foreign atom come and substitutes this host atom here, isn't it? So this defect is actually known as the substitutional defect. So what is meant by substitutional defect? Whenever some foreign atom or foreign impurity is coming into the this atomic arrangement, replacing or substituting the host atom, this is called as the substitutional defect, isn't it? The important thing is that this in substitutional defect, the size of the foreign atom or impurity should be maximum, isn't it? And whenever we talk about this interstitial defect, so here the foreign atom comes and acquires the interstitial voids in this host atomic arrangement. Suppose foreign atom come and will stay in the interstitial sites of these atoms. So this is called as the interstitial defect. For example, we know very well the carbon is present at the interstitial sites of iron. Okay, so if this is suppose the iron Fe, so here the carbon atom go and sits in the interstitial sites of this iron in the steels, that we know very well. So see, whenever foreign atoms come and get position in the interstitial voids of the host atoms, then its this defect is known as the interstitial defect. Okay, substitutional and interstitial. So the thing is that main condition is what? This interstitial जो void है, already it is very small. So the foreign atom or the impurity that is going to come and sit here, it should be smaller than the size of the host atom, and also from the than the size of this interstitial site. So this is the important thing. This condition should be fulfilled. Then and then only this can happen. यहाँ पे क्या होना चाहिए? एटलीस्ट इक्वल, ग्रेटर देन इक्वल टू दी होस्ट एटम होना चाहिए इम्प्योरिटी, यहाँ पे वेरी स्मॉलर देन दी होस्ट एटम. So these are the point defects we have seen. Now let us see what are the next defects after the point defects. So of course we are going to see here the line defects. The line defects, which are also known as the one-dimensional defect. One-dimensional defects. So in this we are having the edge dislocation and screw dislocation. The edge dislocation and the another one is screw dislocation. Okay, so basically if you used to look at this line defects, so what is mean by this line defects? So here the definition of the line defect will be if the imperfection in the material is extending along its length or along the line whose length is much larger than the lattice spacing, then the imperfection or the defect is the line defect. So you are having these imperfections and these are along the line and whose length is much more than the spacing between the atoms or more than the lattice spacing. It is called as the line defects. Now in these line defects we are having this edge dislocation and screw dislocation. So the dislocation is nothing but the defect. Now when you talk about this edge dislocation, which is the defect and which can be the insertion of the extra half of the plane into the regular atomic arrangement, and as this is the extra half in the regular atomic arrangement, this is termed as the edge dislocation. So it is simply what? It is the insertion of the extra half plane, isn't it? So see here, now if you see this atomic arrangement, you can see here there is an insertion of one extra half plane which is here, isn't it? So this is the dislocation. And see, whenever this extra half of the plane, please remember, when this extra half plane is above the dislocation line, or this is the dislocation site, it is this extra half is above this dislocation line, it is called as positive dislocation. And how this positive dislocation represented? By the C. This is inverted T. This line is showing where the dislocation it is, isn't it? So this is the positive dislocation. And if suppose this extra half is present below this dislocation line, okay, like this, like this, so this is the extra half plane which is below this dislocation line. It is called as the negative dislocation. When extra half plane is below the dislocation line, it is called as negative dislocation. Okay, so please remember that this dislocation line can be also referred as, okay, or also we can call it as the Berger vector. So what is this Berger vector actually? So Berger vector, so the Berger vector is also is going to give us the amount and direction with which the dislocation or the extra half plane is moving out from the regular arrangement. So see, we know that when the force is applied, what is going to happen? So this extra half of this plane is going to come out, isn't it? How? So this bond is going to break, okay, when it's coming close and close to each other. These bonds are going to break and the new bond is going to form like this, and in this way this extra half of the plane is going out of this arrangement, and now these atoms are regularly placed or positioned. So this amount, how much distance and direction is given by this Berger vector B bar or B cap. So B bar is this Berger vector. So this dislocation line can also be represented by this Berger vector. And if we talk about the Berger vector for this H dislocation, how to get this Berger vector, so let us see. So see here, you can see here, this is the dislocation, isn't it? This is the negative dislocation I am showing here. Now we want to draw, we have to find out the Berger vector B bar. So how to get that Berger vector? So there are certain rules we have to follow. So how I am going to draw this here Berger vector? So first of all, I am having some rules. So I am using the right hand rule to have the Berger circuit. I'm going to form the loop or the Berger circuit. So I'm keeping this thumb here where the dislocation side is there, this extra half of plane there. I'm putting my thumb here, thumb of right hand, and I'm going to rotate it. So in this direction, the Berger circuit is going to form. This Berger loop is going to form. Okay, and after that I'm going to have this Berger vector from start of the circuit to finish of the circuit. Okay, so in this edge dislocation, suppose I am going to find out the Berger vector. Say I am taking this atom as there is dislocation site. Okay, this is the extra half of lane. So from here, see, I am going, or from this point I am taking here, this atom I am taking here. So I will go left by 2 atoms, 1, 2, up by 4 atoms, 1, 2, 3, 4. Then again at right to the 4 atoms, 1, 2, 3, 4. 1, 2, 3, 4. Then down 1, 2, 3, 4. Then again coming to the completing the loop, 1 and 2. Isn't it? So whether my loop or circuit, see, this is the direction of the circuit. Okay, so let us see here whether this loop is completed, whether circuit is complete. No, so circuit starts from here, it gets finished here. So why this, the distance is remained here, we could not able to complete the loop because of the presence of this extra half plane, isn't it? And see this, now Berger vector, from where to where we are going to give it? From start to finish. So from start I will give start to finish. This is my Berger vector, which will give me how much magnitude you have, or by how much magnitude this extra half of plane is going to move out, and the direction of it, So in the Berger, we have not considered. Okay, so see here, in this edge dislocation, we got this Berger vector, this B bar, in this fashion. Okay, and you can see here, if this is the dislocation, extra half of the plane. Now in edge dislocation, you can see here the Berger vector is perpendicular. See, this is the edge dislocation, and to that this Berger vector is perpendicular to this edge dislocation. Please remember. So in edge dislocation, the Berger vector is perpendicular to the edge dislocation. Very, very important thing. So this is about the edge dislocation. And now I am going to talk about the screw dislocation. Second, that is screw dislocation. So this, it is being assumed that the screw dislocation is formed by cutting the crystal, by cutting the crystal part away through the knife, and it transfer, and the name dislocation is given, and the name dislocation is given because, or as, it transforms the successive atomic planes on a surface of helix around the dislocation. That is why this dislocation is known as the screw dislocation. Let us see the diagram actually. how this screw dislocation is look like. So see here, this is the struck crystal and it is assumed like it is being cut by or cutting part away through the knife. Okay, of course for at each corner there are the atoms. Okay, so this is the screw dislocation. This is the screw dislocation. Okay, so the successive atomic planes are transforms on surface helix around the dislocation line. So it is like this. If this is a dislocation line, so every atomic plane is transferred successive on the helix, isn't it? And this is the dislocation line. Dislocation line. So this is the reason why this dislocation is named as the screw dislocation. Okay, plane, see here, into the surface of helix around the dislocation line. So the name dislocation is given as it transfers the successive atomic planes into the surface of helix. See, the successive atomic planes are getting transferred like helix, okay, around this dislocation. This is the dislocation line. Okay, so you can see here we take the knife and we cut this crystal with this, try to cut this crystal with knife. So this is the screw dislocation. Okay, so this is also the line defect. And if you see here the Berger vector for the screw dislocation, so let us draw this diagram for screw dislocation. So see here, this is the atomic arrangement, and here I can show you this is the screw dislocation, and of course for that we are going to find out the Berger vector. Okay, so that knife mark I am showing here on the crystal like this. So this is the screw dislocation, and say this is the start. From here I am going to start the loop for Berger vector, and if I have this loop, so it will finish here. Okay, so this is start and this is finish. And if I give this is the direction of this circuit, because there is here the presence of the screw dislocation. Now here you will get the Berger vector from start to finish like this. Okay, and please remember this is the screw dislocation inside this crystal. Okay, so if you look at this, so in screw dislocation this Berger vector B bar is what? It's parallel to what? The screw dislocation. Please remember here the Berger vector in screw dislocation is parallel to screw dislocation. screw dislocation. Okay, and when the force is applied, please remember, and when the force is applied to this force, how it is moving? So it is moving perpendicular, it is going inside like this, isn't it? So force is applied in this direction and it is moving inside in this direction. So please remember, the screw dislocation, the movement of the dislocation, the screw dislocation is perpendicular to the applied force, isn't it? So force is applied in this direction and dislocation moving in this direction. Please remember, where in case of the edge dislocation, when we apply the force, this extra half of the plane is moving in the direction of applied force, isn't it? So it is moving, it is coming out from this regular atomic arrangement in the direction of applied force. Please remember, so the movement of dislocation, edge dislocation, is parallel to the applied force, whereas here the movement of the screw dislocation is perpendicular to the applied force. Okay, next, if we talk in the comparative manner, so in edge dislocation we require the lesser amount of force, but in screw dislocation the magnitude of force we require in larger amount. That is a one important difference in the edge dislocation and screw dislocation. And of course, one of the differences, in edge dislocation the Berger vector is perpendicular, in screw dislocation the Berger vector is parallel to the screw dislocation. So these are some important differences between the edge dislocation and screw dislocation. Dear students, so after seeing this point defect, line defect, now we are going to see the planar or surface defects. The planar, which is also known as the surface defects. So basically, these planar defects arises due to the change in stacking of atomic planes, stacking of the atomic planes due to certain things like solidification, or some mechanical or some thermal treatments, or with some thermal treatments. That's why some atomic change has happened into the atomic planes, isn't it? So this is actually the planar defects, and we know that the planar defects are classified into number one, the grain boundary defect, the grain boundaries defect. So let us see first this grain boundary defect. So what is this defect? Grain boundary defect. So this grain boundary defect is basically because of there is a different grains because of the difference in their orientation, isn't it? So for example, suppose in the microstructure I am seeing, of course on the big grains I am selecting here. So if you select this one and this is second grain, so grain boundaries are what? So there is a difference, or these two grains are differ from each other because of the orientation, okay, the grain orientation. And where this orientation mismatch occurs is nothing but the grain boundary. Okay, so grain boundary क्या होती है? जहाँ पे एक ग्रेन के जो एटम्स है ये कुछ कुछ ऐसे डायरेक्शन में है, isn't it? एंड दूसरे ग्रेन्स जिसके एटम कुछ इस डायरेक्शन में है. सो वेयर दिस एंगुलर मिसमैच और orientation mismatch occur, orientation mismatch value is theta. So this orientation mismatch is making the difference between these two grains, isn't it? Now the region of orientation mismatch is known as the region. What are the grain boundary actually? So I can write for the grain boundary क्या क्या है? So it is the region of orientation mismatch. Orientation mismatch, isn't it? And theta is angle of this orientation mismatch. So here at this grain boundaries, as the bond length is more, at the grain boundaries, the bond length is more. If bond length is more, then what will happen? The tempering of the bond is more, isn't it? That is, the oxygen can easily react on this boundary very easily. So there will be the less corrosion resistance, isn't it? Length, so that here, so that bonds tempering is more. And as bond tempering is more, definitely there will be what? The maximum oxygen can get react on these grain boundaries. So there will be the less corrosion resistance. Less corrosion resistance. So these are the things are happening because of these grain boundaries, isn't it? So fourth thing I can mention here, the bond length more, definitely there the energy is very high, energy level is there, high energy level. Then fifth thing we can have the region in this grain boundary region, the low melting point temperature, and in this region, the material is amorphous. So these are the things which are happening because of this grain boundary defect, isn't it? That is, two different grains, why they are differing? Because of the orientation of the grains with each others. That is why this grain boundary is coming into this picture. ओके और ग्रेन बाउंड्री पे क्या क्या हो रहा है? सो एज बॉन्ड लेंथ यहाँ पे ज़्यादा है, यहाँ पे ओरिएंटेशन है, मिसमैच रीजन है, देन मेल्टिंग पॉइंट लो है, एमॉर्फस रीजन है, एंड वन मोर थिंग इज दैट, सेवेंथ पॉइंट आई कैन राइट हियर, देयर इज हेवी impurity concentration. So this is the defect, is the grain boundary defect. After this grain boundary, we are having the tilt grain boundaries. Let us see that tilt grain boundaries. So here the second planar defect is tilt boundary defect. So whenever the theta, that is the angle of orientation of mismatch, is from half to 1 degree, we get this some tilt between the crystallographic planes, and it is known as the tilt boundary defect. See here. So you can see here, this is the crystallographic planes having some tilt, right? And if you have this dislocation here, then if this is our Berger vector B cap, isn't it? So here we can have this theta, that is angle of tilt, we can get here as B bar by H. where B bar is, you know, that is our Berger vector. This H is what? That is the average. H is what? The average height between the dislocations. Average height between the dislocations. And of course theta is in radians. Please remember this. Theta is in radians. So see here, these crystallographic planes are tilted with the small angles. So this is known as the tilt boundary defect. Next defect we are having, that is the twinning or twin boundaries. Twin boundaries actually. You can write the twin boundaries. So see here, whenever the truly crystalline material is subjected to the shear force, what is going to happen? See, this is truly crystalline material. So definitely there will be the region or the slip region, the arrangements of the atoms in the slip position or slip region is exactly the mirror image of the atomic arrangement in the unslipped region. Please see it. Okay, so this is the twin region. So this is the twin direction. So see here, so this is the slipped region, the atomic arrangement in the slipped region, and this is the unslipped atomic arrangement in the unslipped region. You can show here the atoms. So when the force is applied, so the atomic arrangement in the unslipped region is exactly the mirror image of this atomic arrangement in the unslipped region. So this is the twinning actually, and the two planes are here we can have along which this slip is occurred or this twinning is happened. So see, these two are the twin planes. These two are the twin planes, which are nothing but the twin boundaries. Okay, so after deformation, जो slipped region की जो atomic arrangement है, वो क्या है exactly? It likes the mirror image of the atomic arrangement in the unslipped region. This is actually the twinning, and the plane through which, along which this is happened, the mirror is the mirror image we can see. This is one plane and this is one plane. So this is the twin boundaries or known as the twin planes. Okay, so this is the twin boundaries. And fourth defect that we are having, that is the stacking fault. So we have seen about the stacking sequences, like we have seen the stacking sequence like A, then AB, and ABC, isn't it? So whenever there is a dissimilarity in the stacking sequence in this atomic arrangement, of course, then these stacking faults are coming into the picture. And see, these stacking faults are basically results into the anisotropy of the crystalline material. It will also have the increase in the potential energy of the lattice, which will also known as, the name of that increase in energy also known as the stacking fault energy, right? So suppose I am having this stacking sequence like this. This is A, B, C, right? And if I am having some dissimilarity like this, So this is A, B and C here. This sheath layer is having some dissimilarity. So such a kind of defect are nothing but our stacking faults, and they are responsible for, or they are getting resulting into the what? Anisotropy of the material. Please remember that is at a point in different direction properties are different. So these are the stacking faults. So dear students, we have seen what are the classification of imperfection, that is the planar and or the surface defect. We have seen the imperfections in the crystal, which are 0 dimensional, that is point defect, 1 dimensional, that is line defect, 2 dimensional, these are planar or the surface defects, and one more there, that is the 3 dimensional defects. These are nothing but the because of the atoms, some group of atoms, accumulation of the atoms, or in group missing of the atoms. These are nothing but the voids. Okay, but these are the very important as far as our syllabus is concerned. Now see, I am going to discuss about the properties of the material which are depend upon the pure crystal structure and the imperfection or the defects in the crystal structure. So let us see what are these properties. So we are going to see the properties. Please remember, many times you can get the question from this point, that is the properties depend upon crystal structure and the properties depend upon imperfection in crystal structure. So I will group the properties like this: the properties which are depend upon the pure crystal structure and the properties which are depend upon the imperfection in crystal structure. Okay, so let us see which are those properties. Okay, so the properties which are really depends upon the crystal structure are, that is specific heat, then melting point of the material, you can have the modulus of elasticity, coefficient of thermal expansion, then ductility and hardness. Okay, so these are the properties which are depend upon the crystal structure, whereas if you look at this imperfection in the crystal structure, we are having yield strength, we are having fracture strength, then fatigue strength, we are having semiconductivity, then electric conductivity, then we are having creep and work hardening or strain hardening. So how many? So we are having this yield strength, fatigue strength, fracture strength, semiconductivity, electrical conductivity, creep, then work hardening. These are the properties of the material which are depending upon the imperfections in the crystal, and we have seen the imperfection in the crystal are what. Then these are the property like specific heat, melting point temperature, modulus of elasticity, coefficient of thermal expansion, then ductility and hardness are the properties which are depend upon the crystal structure, isn't it? So in this way we have seen in this video the imperfections in the crystals. Thank you.